Okay, welcome everybody to this webinar, 20 years of thermal, looking back at what's been happening. We have two amazing panelists, Carol Lynch from the EPA and David Fleming, founder of TRS Group. Hopefully David is still in here. His computer got kicked out, but if not, he will be in shortly. So I will start us off by giving you guys a little overview of the thermal projects we know of that have happened since 1980. That's actually 40 years ago. So very early on, there was some work done in the Netherlands, a couple of sites with thermal remediation. Then it was kind of quiet for a long time. So we jumped to 1995, and you see a dot for each project. Now there are projects in the US, Fort Richardson up here, heated bio. We got some activity in California. We got a Sandia National Lab, a demonstration in Savannah River site. One of the more noticeable one was the Livermore Gas Pad Demonstration in 1993. You see Roger Ames, Robin Newmark, and Ken Udell, just three of the fantastic brains behind this demonstration. They were doing very sophisticated dynamic underground stripping, combining ERH and steam already in 1993, so 26 years ago. Then a few years later, Craig Eaker from Southern California Edison, Hank Sowers got involved with the other three and others, and designed and cleaned Visalia Pole Yard. This was done from 1997 to about 2000. And more than 1.3 million pounds of mass was removed from these 2 acres underneath this pole yard. See steam generators over here, the treatment system here, and they were able to account for the mass. About half of it came out as what was called brown yucky stuff, or napple. And then, you know, other fractions in the vapor. Some of it was degraded in situ, and some of it came out in the water that was pumped with the 400 gallon per minute system. This Superfund site was delisted, and the groundwater of Visalia could be used again. So it was a pretty amazing project done before the year of 2000. So in 2000, we've got some activities in Europe, Denmark, Netherlands. This is actually in Prague, in Czech Republic. We have had a demonstration in Saipan Island by Shell. And then you see a few more projects starting to cover North America. We go forward 5 more years, or actually that same year, David Fleming, who is in the middle of this picture, and these 4 other guys started TRS. And that's one of the reasons David has a 20-year anniversary this year. 2005, you see a few more projects, one in Germany, and mostly still the US. A couple more projects in Denmark actually occurred. And if you go forward to some of the highlights of that, noticeably the Young Rainy Star Center, which was a demonstration of steam enhanced extraction and electrical resistance heating. There was Steam Tech and Macmillan McGee did this in Florida. TerraTherm did this amazing 105-foot deep cleanup in northern LA for creosote, and were able to again get a closure letter and totally remediate this site. Here's a TRS project at Pemmico Superfund site, electrodes stacked 3 tall to cover a reasonably large subsurface area next to this aqueduct. Some of the more noticeable projects. 2010, you can see Northern Europe, pretty busy with projects. Germany, Uwe Hiester and his Reconcite company is doing work there. We've got England, the Harwell site, and then a lot of East Coast and West Coast projects in North America. Pilot test in Brazil, and one in Japan. These were TerraTherm pilot tests. So some of the more noticeable things, thermal conduction heating used to treat saline conditions right next to the San Francisco Bay, another TerraTherm project. Here's a TRS one next to very sensitive buildings with electrical resistance heating. getting more and more fancy about how we can use the technologies in difficult, tricky situations. So 2015, you can see Southern Europe is starting to get a little bit of some projects. There's one in China and Brazil, 4. You can't see the 2 dots here, but there's 4 in Brazil. And then a lot more again on the West Coast and on the East Coast of the US. Some of those developments led to very routine indoor remediation where we're treating under these big sensitive buildings and everything is under great control. And also, of course, expansion into treating fractured rock. And on the right here, we just see some of the sandstone that can be remediated. There's been more than 15 thermal projects in fractured rock to date. And then, 2020, which is now, you can see kind of where thermal has been done. We've got Europe now, all the way from this north to the south. This is northern Sweden, England, Scotland, Italy, and Spain. And even in Greenland, there's a pilot test going on, treating above grade for some oil contamination at a site up there. Brazil, more than 10 thermal projects, and China has really come to life here. We've got a lot of projects around Beijing and Shanghai, and then we have a couple in Vietnam, the Da Nang one, and then a pilot test at Bien Hoa. And we've had a pilot test in Korea, also done by Terratherm, and a couple of projects in Japan. And finally, one in Melbourne, Australia. So it's starting to really get traction all around the world. And you can see here where the hotspots have developed for thermal treatment. And then I'm gonna hand it over to Kira. My first question is, we know you're a very brave lady, and I remember the first thermal project you ever got involved in, and we would love to hear some about that, please.
Thanks, Gorham. So yeah, on the heels of Visalia and the success we saw there, one of the things that happened is that we had a couple of wood treater sites that at the time I was working for the Corps of Engineers that we were supporting EPA on. One is in Region 10, the Wyckoff site, and then we also had another large wood treater site in California, McCormick and Baxter. Both of them have millions of gallons of NAFL. The state had approached EPA on both of those sites saying, isn't there something that we can do that's different than just strapping us with years and years of O&M? And at the time, I think I saw Jim Cumming as one of our people that are listening in today. He had approached me and said, let's look at using thermal treatment on these wood treatment sites. And we put together a panel of experts, knowing that really we did not have the experience on some of these technologies. We had an excellent group of people that helped to have us look at these 2 wood treatment sites. We moved forward with a pilot on Wyckoff, and you can see the Wyckoff site here. We actually have a sheet pile wall around the outside. It's about 8 acres. What you can see on the inside there, kind of mirroring the same angles as this actual sheet pile wall, is the area that we had identified for a thermal treatment pilot where we were looking at steam injection. We had a lot of lessons learned with this pilot. It was definitely one of the most difficult sites that we could probably pick. And we did not proceed past the actual pilot on this site, but we learned a lot. We learned a lot about the process of designing these systems. One of the key things that we also learned about was the importance of kind of understanding the material that we would be heating up and how that would be impacted. And so one of the things that really was one of the factors that made it so that we had to kind of shut down our pilot on this site. And Gorham, if you can show the next slide, where one of the things that we found is that when we heated up the naphthalene at the site and changed the temperature of it, that we had some significant issues with that clogging up the piping, and that really ended up having it be so that we had to end the pilot itself. But I think the good thing is that it definitely raised the, at least for myself, my own education on how we can use thermal treatment on some of our projects, and really was the start of us looking at this at many more sites.
Very good. So David, right around the same time, you were contemplating starting a business, weren't you? Can you tell us a little bit about that and how that felt, please?
Sure. So, starting any company, there's risks, inherent risks, right? These are 4 of them that I could think of right away. Legal, we were faced a lawsuit right as we started the company. And fortunately, that lawsuit turned out to be in our favor, and we were able to move freely into the marketplace with in situ thermal remediation. Financially, it took, digging into our own pockets to come up with some money, even at a time when, we didn't have a lot of money, and it didn't take that much, but we did need to dig deep in to invest the same amount, the 4 of us, into the company. We also had the benefit of a venture capital company helping us, even in the face of a lawsuit, and the Small Business Administration also invested in the company early on by providing loans, as well as actually being an investor in the company. And then just, the risk of professionally risking your career. There was no guarantee it was going to work. And so we were all rolling the dice. We think this is a good technology. We think the market will respond, and let's take the risk and go with it. So we were willing to do that. And then, of course, personally, we all had families with young children at the time, and we started it 20 years ago. So there was a tremendous amount of time, as you can imagine, commitment to making sure that it worked, and that we were able to form it and build a successful company. And lastly, a quote from Abraham Lincoln I really like. I think persistence and being resolute in your vision and what you're up to is really key. And in some cases, according to Abraham Lincoln, the most important thing to succeed. And I really believe that and live by that. And some major learning experiences. I came up with these 6 that I wanted to share with you all. The top one being building a team. It's so important to have the right team and to surround yourself with people who can provide areas, disciplines that I don't have or others don't have expertise in. And also being on a team where everybody's on the bus together, moving in the right direction. The commitment to the vision of rowing the boat together, for a common purpose. And of course, relationships, we're in a relationship business. Relationships are built on trust. Trust is difficult, takes time to build. It's easy to fracture and tough to build back again. But relationships with our staff and our customers, very important. And I place high value on building relationships and having a vision. Having the vision of I wanted to be part of a company that created opportunity for other people and that provided a value to the marketplace and opportunity that inspired our staff, to get up in the morning and go to work so that they could also learn and grow and feel like they're making a difference in the marketplace as well and be rewarded for their hard work. And so that's what we've created. Persistence, once again, it takes persistence to stick to it. When times get tough, you got to dig deep sometimes, but I think that helps to be persistent in order to succeed. And you've got to have value for the marketplace. And one of the really neat things about our company, and this comes from our leadership almost from the beginning, and I got to call out Brett Trowbridge, who's our president and CEO, who has helped really guide the principles and the strategies of our company, one of them being focusing on each other's highest value that we each provide to the company. And that to me is inspiring, and it helps me get up out of bed in the morning to go to work, knowing that I can make a difference in what I really like to do and what I'm best at doing. And then the last thing is, in terms of learning experience, is gratitude, being thankful and grateful for all of the people that have made this possible. There's been a lot of people who've been involved in this company that have helped me and helped each other to succeed. And then finally, I wanted to end with the Dalai Lama's quote. You know, I think one of the elements that defines all of us is how we treat other people. And it's possible, whenever possible, be kind. And it's always possible to be kind. So that's something that I try to live by and that I have learned more about being part of TRS.
All right. So it wasn't always easy, David. I know of one of the first projects, the Fort Lewis one, that was pretty big. And when I was with a different thermal company than you, we tried to win the work, but you won it. Can you tell us a little bit about that project, please?
Sure. So Fort Lewis, Eastgate Disposal Yard in Tacoma, Washington, the Army base. They're now called Joint Base Lewis-McChord. But what we're looking at here is the treatment area. So this was a NAPL had been defined source areas, 3 different ones. We're looking at 2 of them, NAPL area 1, 2, and 3. And we're looking at the co-located electrodes with the plastic oversleeve, CPVC oversleeves on them. There's also a co-located recovery, both vapor, steam, and free product recovery well is co-located in that electrode. And then the blue strings you see there are thermocouple strings, and then the equipment compound off in the distance in the back. 4 takeaways that I wanted to share with you all from this that really helped, I think, help develop and propel in situ thermal remediation to advance in the marketplace. The first one, and Kara Lynch was really had the vision for this at the very beginning when she was at the Corps of Engineers. And so, a lot of thanks to Kara for helping with this. But the first one is being flexible with your contracting and being flexible with your performance objectives to take into account changing conditions in the field that you did not expect as dramatically as some of them here, like fast flowing aquifers. Being willing to make adjustments in the field to mitigate those type of change conditions. The second one was the concept of mass flux or discharge, mass discharge off of a source zone into a down gradient plume. And in this case, how thermal interacts with that mass flux and can help mitigate mass flux in the down gradient plume. And Mike Annable from the University of Florida, through an ESTCP funded research and development project, performed a mass flux study at this site that I think really helped set some of the ground work for using mass flux as a performance objective in the future. And then the third one had to do with another ESTCP project that CDM Smith was part of, which, by the way, CDM Smith was a contractor doing construction on this project with us, and AMEC was another contractor who did data management and reporting. But that third takeaway was looking at the effects of the heat in the subsurface generated by in situ thermal remediation and the effects that heat can have on the in situ destruction pathways of bioremediation. And so CDM Smith did an ESTCP project to study that effect that really helped, I think, set the groundwork as well for future projects, harnessing the heat for that purpose, increasing the kinetics of the bioremediation pathway. And then the last thing, the fourth one, was the level of achievement of contaminant reduction that we achieved at Fort Lewis was well beyond expectations. In this case, you're looking at a 49% reduction of TCE in soil samples. And nobody expected that high percent reduction, but we did show that it's possible. And I think, 15 years later, we continue to see those high levels of contaminant reduction. And then on the groundwater side, on the next slide, Gorm, this is a graph showing you TCE concentrations in microgram per liter on the y-axis. And on the x-axis, it's time by year, January to January, from 02 to 08. And the four colored lines on the graph represent average concentrations of TCE in different monitoring wells in the three different treatment areas, area 1 being magenta, area 2 being the red line, and area 3 the brown line, and then the green line is other monitoring wells. But a couple of things to look at here. On the very bottom, you see these horizontal lines that are color-coded with the lines above. And those horizontal lines represent the operating time frame for each treatment area. So, for example, area 1 operated from just before January 2004 to 4 to 6 months later. But the other thing to note here is that, and this is pretty consistent, this response from three different areas. You see an increase in the TCE concentration in groundwater right at the beginning. That's because you're starting to boil the TCE. You're seeing desorption occurring from the TCE coming out of the soil matrix, coming out of the NAPL. So you see that initial increase, but then you see that corresponding decrease as you continue to heat and steam, strip, and boil. You see that decrease, and that happens at each of the three areas. And then the last thing to take away from this is that even after you stop heating, and in the case of NAPL area 1, several years later, you see continued decline in TCE concentrations in the groundwater without heating. But there is retained heat in the subsurface that is increasing the kinetics of the bioremediation in situ destruction pathway, resulting in significant decreases. And we now see this 15 years later, at just about every site that we work on, this same type of response occurs.
All right, thank you, David. Kira, I know you've also done a site where it wasn't all bio and it wasn't all thermal. Can you tell us about that a little bit, please, and you know how you see those two technologies working together?
Yeah, so I think one of the things that I have really learned over time, and I think when we were contracting Fort Lewis and we were looking at that, you know, we were really thinking about source treatment from the standpoint of just applying thermal, right? And, you know, despite the fact that David was talking about the flexibility that we built into Fort Lewis, I think that's one of the other things that we've really learned is that we thought we were being flexible at Fort Lewis with the way that we are contracting, but we were very focused on, we had defined the boxes that needed to be treated. Our contracting was relatively rigid in that, you know, we thought that we needed to meet a certain temperature. We also thought that we would pre-negotiate up front. We needed to have unit costs for ongoing treatment passed when we hit the temperature. And I think one of the things that we've learned is that we don't need to have that kind of rigid approach, either on the contracting or how we apply these technologies. And that also that when looking at how are we going to manage our source treatment, how do we get sufficient source strength reduction so that it can be paired up with a plume management strategy that reduces having to be out there for active treatment, that we need to look at how do we combine the technologies, and that thermal has areas that it makes sense to target with that technology, but many times there's lots of benefits of looking at other technologies for managing other parts of the source that should be targeted for some sort of active treatment. And time oil is a good example of that. I think the other thing that time oil within this time frame, the other thing that we were learning was the importance of really having a better definition of our conceptual site model from the standpoint of where the contaminant exists relative to the subsurface stratigraphy. And I think we've always known that conceptual site models are important, but in this time frame, the tools really evolved. We started to do a lot more three-dimensional visualization. You can see from this picture here how we use that to then look at where it made sense to combine technologies for the time oil site. We had areas of the site that we were targeting with thermal treatment where we knew we had contamination throughout a much thicker area where we had contamination in multiple different stratigraphic intervals. And then we had kind of a warmer area of the plume where we knew we had some NAPL associated with a low permeability zone, but it was very thin, pancake-like. And I remember one of the things that the ITAP panel always taught me from the very beginning when we were looking at costing and evaluating thermal treatment is that when you have a site where you have like thin, pancake-like contamination, that those are the ones that maybe it doesn't make sense for looking at thermal treatment because you've got like a widespread contamination over an area where you're targeting a very thin interval. And I think that's where really looking at some of the other technologies like in situ bioremediation and partnering that up with a thermal treatment makes sense. I think the other thing that we actually learned as part of the Time Oil project is that, you know, after we completed the majority of the thermal treatment in the area that we had identified as this kind of the main core of the DNAPL contamination, is we started to see that there were smaller hotspots within the actual the area that we had identified for bioremediation that would really benefit from some additional treatment in addition to just trying to look at enhanced bioremediation in those areas. With the way that we had set up the contract on this site, we were working with both TRS and CDM. We had the flexibility in that contract to kind of look at innovatively combining the two technologies. So I think this is the first project that I worked on where we looked at using heat, but using a very different approach for getting the heat into the subsurface and more targeting the 35 to 40 degree range with the concept that the heat would enhance the bioremediation in that area. So I think that was a real turning point for us on looking at not only could we combine these technologies from a spatial standpoint or a temporal standpoint, but that we could actually overlap them in ways and optimize both technologies. So this is just a picture to show you. This is the Time Oil site. We had the thermal treatment zone and also the bioremediation zone. They were directly, basically adjacent to each other. And we really started with the thermal treatment, but in the end, there was a lot of overlap even with the timing of applying both technologies on this site.
Thank you very much. Hey, one thing I forgot to mention to every one of you out there is there is a bar up on top of your screen that can drop down, and there's a Q&A button. And we welcome you to put in some comments or some questions. In about 5 minutes, we will be done with this kind of formal introduction, and then we can take questions. I see there's a couple of questions in there already, but please go to the Q&A place if you have some also. So I'm just going to highlight a few improvements in thermal technologies. One of the main things that I've noticed is 20 years ago, there were 4 or 5 thermal companies and they all had just one technology, right? SteamTech was steam, for instance, and TRS was ERH and so on. Shell and Terratherm was thermal conduction heating. What's evolved is much better understanding that a site can be very complex and sites are totally different. So in order to master thermal remediation, it's a great idea to have more than one technology. 2 or 3 of them is what you need in your toolbox if you can have a good solution for most sites and for sites top to bottom. Sometimes you have a very tight top and a very permeable bottom, and one technology can't do the whole thing. So what you see up on the upper left is kind of a sweet spot type of overview where ERH, steam, and TCH kind of overlap in some areas. And then there are just other conditions where you just have one option. So that's one thing that's really developed. We're no longer one-trick ponies in this industry. At the bottom, you see similar type of subsurface being remediated on the left in 2002. And on the right, just a few years ago, you can kind of see value engineering has made it to where we've simplified things. We use less exotic materials, not as much stainless, not as much wrapping of pipes if we don't have to do it. So we have made thermal remediation more robust and also more affordable over the years. That's a major thing that continues to go on. Value engineering, trying to be more cost effective and more sustainable. Then we have gotten very good at operating next to sensitive things, including, as you see in the right upper picture there, that's an ERH site in Brandywine, Maryland. ERH was being conducted underneath these railroad tracks and underneath an active road while nothing was shut down. And there was very detailed subsidence monitoring. The tracks had these prisms on them, and we were able to show that they didn't move substantially. So thermal has come a long way in getting more cost effective and being applied under very challenging conditions. One of the things we always struggled with in the beginning was predicting duration and how much energy we would need. Most of the time we did some predictions, and then some sites we were spot on, others we were pretty far off. So that's one thing that really developed, is we now can basically put in a computer the conditions of a site, and we can simulate what's going to happen. On the left, you see an energy balance where power goes in, and there's heat losses, and there's heat removed, energy removed. On the right, a cumulative curve where we are predicting how much energy we will need at the end. And of course, getting better at predicting these things, and we're now typically within 10% of what we end up seeing in the field. That helps a lot when you're trying to convince someone to pay for it. And then finally, data visibility. We don't want it to be a mystery what happens down there and how we're doing and how we're getting to the project results. We have data management, data collection. Most of it is automated, and you can now see, almost like when you're driving a car and you're looking at your speedometer, you can see, how fast you're going. You can see somewhere how far you've gone. The same thing here. We want to make it very clear how much of the operational budget we've used, how much of the energy we've spent, and where are we in return for that? What are the subsurface temperatures? How much mass is coming out, and what's the rate? So making that data visible to our clients and consultants has been another major step forward. And so I have another question for you, Kira. And that is kind of, how have the approaches to contracting thermal and selecting thermal evolved over time?
So really, I think one of the contracting approaches have really mirrored the same, what I would call kind of our desire to allow more and more flexibility that we've seen also in the way that we're designing these systems. And I think when we talked about Fort Lewis, we really moved forward with this idea that we had to have a very strict area definition, very strict controls on, how we were going to assess contract performance and unit-based definition. Time oil, we moved away from that a bit, and I think one of the most recent projects that I'm working on, this one, Hamilton Road Impact Area, we have really tried to take that flexibility in the contracting approach and also in the way that we're allowing the remedy to proceed to even allow more flexibility than that. You can see in this picture here with the way that we set up the rod, and this is designed, all of the area where you see the yellow dots, that basically is the area that is generally targeted for the in-situ thermal. The blue dots are representing area that in-situ bioremediation is being done. And then you can see the red line of monitoring wells right there along the edge. That is a line of monitoring wells where we are going to be looking at a flux-based measurement, both pre-treatment and post-treatment. And the way that we set up this contract and that we envisioned proceeding with this project was to not put any constraints on the application of these technologies and allow complete flexibility with the way that they were implemented, with really the goal, the driving goal being to achieve a mass flux reduction goal in that down gradient flux line. And in focusing just on what our final goal is, which is that flux reduction, allowing for the construction and the implementation of this project to proceed with as much flexibility as possible. So the design that has been put together, especially for the thermal treatment, has been a combination of thermal technologies. If you can show the next slide, Gorm. One of the things that we've done on this site is that they are going to be using both steam enhanced extraction and ERH. And they're targeting that for different stratigraphic zones in the site. So it's very much like the schematic that Gorm showed a few slides back, where he was talking about kind of combining the various technologies based on the specifics of what we know about the site. So I think that's, really one of the biggest lessons learned that I have had over the last 20 years in applying these technologies on a lot of different sites, is that the more flexibility that we can allow in the way that we design and implement these technologies, and the more that we can understand about where the contamination is and how that's impacting transport, the more we can optimize the application of the technology itself.
Very good. And because we don't have all that much time left, I'm going to now go to some of the questions that have come in. The first one, David, I think is for you. And it's from Rasmik. He says, do you have any success treating PFAS in soil and groundwater?
Yeah, as a matter of fact, we do. We are in the process of validating both a PFAS treatment in soil using our thermal conduction heating technology. We've recently been awarded an ex situ treatment pilot test through ESTCP, as well as an in situ pilot test, one for the Air Force, one for the Navy. So we have demonstrated this in the laboratory with very good results, greater than 4.9% reduction through volatilization, not through destruction, but through volatilizing the PFAS from the soil. So we're in the process now of building those projects, starting when they just got contracted in the last couple of weeks. And then we're also working with our European partner, Cornelsen, to bring the perfluoride technology into the United States and North America to treat PFAS in water. Not in situ, this would be done ex situ. But we've also been recently awarded a project with the Navy to test this, validate it, and treating AFFF, PFAS-laden aqueous film-forming foams for the Navy. And we'll also be doing a project for the Air Force, so we're working on the contract for that now as well. So we have solutions for both PFAS in soil and water, and we're in the process of validating them in the United States.
All right. Got one for Kira from Dawn Rigger. What do you see in the future for in situ thermal remedies for EPA Superfund sites? Essentially, he's asking you to predict a little bit here.
Yeah, well, I think that at least it's very telling to the fact that I know from my experience, and I've talked with others, I don't think I see a single feasibility study coming in now for a site where we've got a significant DNAPL source zone that doesn't at least consider thermal treatment technologies as part of the FS. And I think that we have examples of where we've implemented full-scale in situ thermal in almost every region at this point, and a lot more sophistication that we're beginning to see with the feasibility studies that are coming in, with people understanding how to really combine technologies. I think that's going to be the key moving forward. is being able to look at how we can combine technologies to be able to make the source treatment cost effective enough and be able to show that return on an investment to be able to convince the people that need to be able to pay for some of this that it makes a lot of sense to do that active source treatment up front and to not have to have these long-term liabilities associated with, assuming that you could do some sort of containment or something else. So I think the more that we can look at optimizing these technologies, actually the importance of doing source treatment, I think we're beyond the point where really the industry is questioning that anymore at this point. And I think it's a well-known fact that in situ thermal treatment is really one of the most effective ways to deal with significant source areas in a reasonable time frame.
All right. I have a question from Dennis Conley, one of the good old boys, had also helped invent the thermal technologies. And his is, at the time oil site, did you use MBTs to identify any shift in the microbial population and diversity of species?
We didn't at the time that we were doing the actual design of the in situ bioremediation. We were really focused on using amendments that could result in enhanced mass transfer. But we have done some of that work now post source treatment to look at the long-term plume management strategy and what we're doing as far as being able to show that now that we're done with the source treatment at time oil, to be able to document that we have sufficient source strength reduction to be able to support an M&A alternative for that site in the long term. So at the time, I think that we were actually looking at the in situ bioremediation in the source treatment area. We weren't really focused on understanding the microbial communities specifically there, more on how we could optimize the actual amendments that were being added in different areas to facilitate mass transfer.
All right. So us thermal guys are always kind of trying to push the limits. There's a question that came in from an anonymous one, and it is probably for you, David. Can you provide any insights on issues if you're trying to treat DNAPL, which is 70 feet below the water table, and what do you do? And then another of his questions is what if it is next to a building, but DNAPL as much as 70 feet below water, how would we do that, and have we done that?
Well, I guess there's a couple of things, one of which could be hydraulic control may be necessary depending on the water movement, the velocity of water movement. We did that at Fort Lewis, hydraulic control to slow down that water movement and make sure we're capturing inside the treatment area. But, with the design elements of temperature over time, we're boiling the DNAPL, depending on what the DNAPLs consist of. I'm thinking of a chlorinated solvent DNAPL, like a typical one that we've treated, raise the temperature in the subsurface to the boiling point of that compound, and we now are creating steam and vapors, and we have the site under vacuum. We've got also a permeable backfill in our electrode borehole that creates a preferential pathway for vapors and steam to move upward. Even bubbling up through if you think of like a can of Coke, you open it, those little bubbles in the water, the carbonation, similar to that, bubbling up into that permeable backfill. And then once we get up into the vadose zone where we've got vacuum, we're able to harness buoyancy and as well as vacuum to recover that material. So that has proven to be successful on many DNAPL sites by many different thermal in situ thermal vendors, and so that's, I think, the main approach. And Kira, Gorm, if you have anything to add to that, please by all means. But then on the last part of the question too, buildings, we have done now dozens of in situ thermal remediations, either under buildings, some of which have been occupied, or under other structures without damaging the buildings or the structures, and being able to maintain, safe air quality, both inside the treatment area, inside the building, outside the building, where it's monitored to make sure it's being maintained. So it's been one of the big lessons learned over the last 20 years, is that you can apply this technology safely and effectively in public areas.
All right. Yeah, one of the complexities I would mention is, for the first part of the question, if you're treating DNAPL that is very deep below water, how it depends on how clean you need to get what your objectives are. In some rare cases, you may be able to just heat that interval and extract on it and capture that steam. But more typically, it isn't quite that deep below water. And what we end up doing, I think most, if not all, the thermal guys will say you have to treat to the top of the water table and make that hot enough that the DNAPL cannot recondense. And that does expand the vertical interval that you need to heat, and it increases your energy usage, but it also ensures that the vapors and the steam generated can come up into the base of the vadose zone and get extracted up there. It's a lot more difficult to get vapor capture below water, where you don't necessarily have open screens. So there's a few more questions. Some of them are very, very specific to bio. We will try to answer them with written responses. The final one that I see is essentially, so with 40 years of thermal development, and the last 20 years where it's really moved fast, how big can you make these? Is there like an upper limit to how big thermal sites can be? And interestingly enough, we had this as a backup slide. I'm just going to show, one of the larger areas that we know of. This is a site TRS is doing in Suzhou, China, not far from Shanghai. On the left, you see all these containers, gray containers. They're power control units, each of them feeding hundreds of electrodes. And you can see this, the magnitude of this site. You see those gray knockout pots removing water from the vapors, 5 more control units for power there. And again, on the other side, more power control units. Each of the little white mini towers you see is basically a group of electrodes. And this site has more than 3,000 electrodes to heat, simultaneously. So that kind of gives you an idea of how far we've come and how we've been able to develop this technology, not just to get more surgical and more tricky and better for difficult sites, but also how you can scale it up. And and this project was built in less than 1 year, and it's operating right now. So that's just an example of it, how it's possible to scale these things up if you have a big enough site to treat. So that's essentially the end. Let me check for more questions. Oh, there's a few more. Yeah, and a good comment from Jim Cummings. Visalia went to 130 feet with steam, well below the water table, and that was also a DNAPL site. Absolutely correct, Jim. It even went to 145 feet after they found that there was a little more mass below the second or third aquitard there. At that site at Visalia, essentially it was treated in layers, and with steam, steam was pushed from injection wells to extraction wells, and then below the aquitard, you got steam breakthrough, and you were pushing NAPL to the extraction wells and then doing pressure cycling. Some of that steam ended up migrating up through the aquitards and helping the zones above it, but that's absolutely another example of successful treatment of DNAPL. way below the water table. I believe the water table in Visalia was 30 or 40 feet below grade, so it was more than 100 feet below water at the deepest location. And then there's another one. Can you provide, from Tom McGowan, can you provide a range of costs per ton of soil treated? That's probably for you, David.
Well, that's a very site specific, right? I mean, contaminant specific, a lot of things to account for there. And I think the correct answer is to perhaps, I don't know if you have a range on the top of your head, Gorm, for that, but I think from rule of thumb, 99% reduction of TCE, you know, on a large scale. See, that's the other thing, economies of scale. So you've got to take into account the size of the treatment volume. Smaller treatment volume is going to have a higher unit cost, lower overall cost. And the opposite's true for the larger volume, right? Lower unit cost, higher overall cost. But it's so site specific. It's difficult to give a price that, you know, will be accurate for every site. And so I hesitate to do that. But I can tell you this, we have seen very large sites with very low unit costs that can get down to less than $50 a cubic yard, but we're talking very big sites, very big volumes.
Like the one on the screen.
Like the one on the screen.
One in China, yeah.
And then the opposite can be true. If you're looking at a very small site, you know, less than a half an acre, and on a pilot scale, you know, a few hundred cubic yards, you're talking, you know, 10 times that easily. And sometimes, and so it really depends on the site. And
yeah.
But I'm happy to talk with you offline, and you know, we'd love to model your site to give you a specific cost proposal, and love to do that for you, talk with you. So if you're interested in that, let us know. Thank you.
All right, we will conclude now. I will just remind you that the next webinar in this series will be with Eva Davis of the EPA. She has been investigating, researching thermal, you know, since way before I started in 1995, and I met her in Oklahoma at the Kerr Lab. She'll be a guest star with our own Emily Crownover, and that webinar will focus on power delivery, power density, energy density, basically the math and science around how you measure how much power you need and how you get it in the ground, how you monitor it and optimize it, and how that matters. That webinar is on November 4th, probably also at noon Eastern time. So we will be sending out a notification for that soon, and we hope to see you again soon. Thank you very much.
Thanks everybody for attending. Be safe.